In this video, I'll be going over our study guide for Exam 2, which covers chapters 5, 6, and 7. So here are the chapter 6 concepts. You'll want to make sure you understand what they mean and know how to calculate or perform them. And so the conceptual questions will be very similar to the quiz questions or the practice exam, where you'll be presented with a situation and you'll need to identify which distribution applies. There will also be quantitative questions which will explicitly state which distribution applies so that you can use the applicable formulas. Let's look at problem number 1 for chapter 6. The time failures for an electronic component are exponentially distributed with a mean of 50 hours between consecutive failures. What is the probability that a randomly selected part will fail in less than 10 hours? Recall, I structure my problem so that you pull out the specific components you need before we even touch Excel. So in part A, it asks, what is the lambda? So in chapter 6, to find the lambda, we're going to take 1 divided by the mean. In this case, the mean was given to us at 50 hours. So 1 divided by 50 is the same as saying 0.02. And you can use Excel or a calculator to solve this. Or you can even leave it in fraction form. I'll accept that as well. But if we look at the Excel file that I've provided, and we look at the exponential distribution formulas, I also have a note right here to remind you that the lambda used in our Excel formulas here is the same as 1 divided by the mean. In part B, it asks what is the value of interest, or A, that we're trying to solve. In Excel, it's referred to as the X. So the thing that we're interested in solving is based on the less than 10 hours. So that's why the answer is 10. Knowing these parts A and B will allow us to then solve part C, which asks, what is the probability that a part will fail in less than 10 hours? So I'll go over to the Excel file, and we're doing a less than scenario. And as a reminder, down at the bottom are the notes to remind you what kind of formulas to use for which scenario. So to find all values less than or equal to some number, then we'll just use the formula and make sure that it's cumulative by typing in true. So since it's a less than scenario, we're going to use this one right here. And I'll type in equals exponential.dist parentheses. The X was what we identified in part B, so that's my 10 hours, comma. The lambda is the 1 over the mean, so I can type in 1 divided by 50, or I can type in the decimal version of it at 0.02, and then I'll make sure to type in true. Closing the parentheses and hitting enter, I get 0.1813. And I'll put the work right here on the study guide for reference. Let's go ahead and do problem number 2. The money spent on food per visitor at Legoland is normally distributed with a mean of $32.50 and a standard deviation of $10. In part A, it asks what is the probability that a randomly selected park visitor will spend less than $20. So looking at our Excel file, we're doing normal distribution right here. And in part A, we're doing less than 20. So I'm looking for the less than scenario. It's going to be this first formula here. So I'll go ahead and type in equals norm.dist. My X is going to be the 20. The mean that was given to us in the story was $32.50. And the standard deviation given in the story was the $10. I'll make sure to type in true and close my parentheses. And then when I'm ready, I can hit enter. And I get 0.1056. In part B, it asks what is the probability that a randomly selected park visitor will spend more than $40. So looking at the Excel file, this is a greater than scenario. So anytime it's a greater than, it's always 1 minus the formula. So I'm going to be using this formula right here. So typing in 1 minus norm.dist, I'll put in my X of $40. That's the thing I'm interested in solving, comma, the mean that was given to us of $32.50, comma, the standard deviation of $10 given to us in the story, then comma, true, and close my parentheses to finish the statement. And then when I'm ready, I'll hit enter. And that gives me 0.2266. So now you might have been wondering why we didn't manipulate or go up or down on the X values. We just used whatever X we saw. Because in chapter 6, these are continuous random variables. These are variables that we cannot count. Rather, we measure them. So I can measure money and I can measure time. And when I measure, that includes all possible numbers, including decimals. So it doesn't make sense to try to count decimals. We would measure time or money. And so you do not need to go up or down, because what's more than $40? It could be something as simple as $40.01 or $41 or $50. So that's why we do not modify the X. We just plug in whatever number we see. So I plugged in the 40 for more than 40. I plugged in the 20 for less than 20. And same with the exponential distribution for the value of interest. Less than 10 hours, I just use the number 10. I don't have to do anything to the X values, just plug them in as you see it. Scrolling down to chapter 7, here are the concepts you need to know for this chapter, and you need to know how to calculate or perform them, as well as the concepts or theories behind them. So let's look at problem number 1. Suppose the speed commuters typically drive on the 5 freeway is normally distributed, with a mean of 75 miles per hour and a standard deviation of 10 miles per hour. If 16 commuters are randomly sampled from the population, solve the following. So the way I structure my problems is to make sure that we follow step by step in the process. So in part A, we're going to be solving for z values. We're going to convert our x's into z's. And then in part B, we'll find the probability of a particular event. In part A, it asks what are the z values for 70 miles per hour and 80 miles per hour. So here's our formula that we're going to be using. This is how we convert a sample mean into a z value. So on the top in the numerator, we're going to take our sample mean minus our population mean. In this case, our sample means are the 70 and the 80, and the population mean was given to us in the story at 75 miles per hour. In the denominator here, also known as the standard error, that's the population standard deviation divided by the square root of n, our sample size. So to convert the sample mean of 70 into a z value, we'll plug in the 70 in the front minus the 75, and we'll divide that by the standard error, which is 10 over the square root of 16. Similarly, to convert our 80 into a z value, we'll plug the 80 where the x bar sign is, and then everything else is the same. It's still minus 75, and then dividing it by the standard error of 10 over the square root of 16. And when I plug these into my calculator, we get -2 for the 70 and +2 for the 80. And you want to be careful when you plug this into your calculator that the top and the bottom are solved separately and then you divide. If you try to enter it straight from the top down, then you're going to mess up in the order of operations, and then you'll come up with a completely different answer. So you want to make sure to try it on your calculator and practice it to make sure that you get the same answer as what you see here. Now I'll show you how to do the same thing in Excel. So here on the Excel file, there is a tab called Chapter 7. So please make sure to find the tab that says Chapter 7 and use it. A common error that students will make is they will stay on the Chapter 6 tab and use the Chapter 6 formulas for the Chapter 7 problems. So you want to avoid that silly mistake. Make sure you're on the correct tab. And what we're going to be doing to find our z values is to use this standardized formula here that we learned back in Chapter 3, with a slight modification though. Because our standard deviation in Chapter 7 is the standard deviation of sample means, or the standard error, we have to take the population standard deviation and divide it by the square root of n. So make sure there's this extra piece in it. So I'll show you how to do it for the 70. So I'll go ahead and type in equals standardize, and then my x is the 70 that I want to convert, comma, the mean that was given to me in the story at 75 miles per hour, and then the standard deviation is the 10 given to us in the story, divided by the square root of n, so that's square root of 16. So I'd type in SQRT for the square root, and then type in the 16 for my 16 commuters, and then close my parentheses, one around the 16 and one around the entire standardized formula, and I hit enter, and I get -2. Let's go ahead and do the same thing for the 80. I'll type in equals standardize, and then for my x, I'll put in the 80 that I want to convert into a z value, comma, the mean that was given to us in the story, which was 75, and then the standard deviation, again, remember that's the standard error. I need this bottom part of my formula here, where I've got the 10 divided by the square root of 16. And then I'll double check and look at all the numbers and make sure they look right, and then when I'm ready, I'll hit enter. And that'll give me 2 for my z value. And you might have noticed that the decimals are different. It's just a formatting thing. I can always fix that using the number menu and then moving my decimals as needed to where it looks right or they're consistent. And then in part B, what is the probability that the sample mean miles per hour will be between 70 and 80 miles per hour? Before you can even try to solve for the probability, we needed to convert our sample means into z-values. That's why I had you do the part A first. So looking at our normal distribution formulas, I do have a note here to remind you, hey, find the z-value first and then plug it into the appropriate formula based on your scenario. In this case, we're looking between two values, or we're working with two z-values. So we're going to use this formula right here because you can see there's two z's. And I'll go ahead and type in norm.s.dist. And we always want to put the bigger z-value first, so I'll put in the 2, and then comma, true, and close out the parentheses, and then type in minus, and then do the same thing again, norm.s.dist. But this time my z-value is the -2, the smaller z-value. Make sure to type comma, true, close the parentheses, double check I've got all the right formulas and numbers in the right place, and then when I'm ready, hit enter. And I get 0.9545. Scrolling down, we're going to do our very last problem for Chapter 7, problem number 2. The proportion of Georgia peaches that get damaged during shipping is thought to be 0.10. To check this, a random sample of 100 peaches is selected and 16 peaches are found to be damaged. What is the probability of having 16 or more damaged peaches in the sample? So here's the step-by-step process to walk you through it so you don't miss any components. Part A asks, what is the population proportion, or lowercase p? That's given to us in the story at 0.10 in the very first sentence. In part B, what is the sample proportion, or p-bar? Recall that to find the p-bar, that's going to be x divided by n, which in this case is the 16 peaches that were damaged divided by the sample of 100 peaches that we randomly chose. So that's how we get the 0.16. Remember that proportions are just another way of talking about percentages, so they always have to be in decimal format. If you were simply to say 16, that's not a proportion. 16 is just a count of something. It's the number of peaches. But I don't know what it's a proportion of. Is that 16 peaches in 20? 16 peaches out of 100? 16 peaches out of 1,000,000? They're very different proportions depending on the sample size. So that's why we have to make sure we do 16 divided by 100. In this case, the 100 is our n. In part C, you'll now want to plug in the variables into the formula and solve for z. So plugging in all of our variables, my p-bar was the 0.16, so I put that in the front. My p, or my population proportion, was 0.1, so I'll put that here. And then in the denominator, where we have the square root, we'll make sure to put our p's of 0.1 where they belong and the n of 100. And then I'll go ahead and solve. And so you can check against your calculator because order of operations matters and everybody's calculator is a little bit different. I'm going to solve the top first. So the sampling error on top is the p-bar minus p. That gave me 0.06. And the denominator, when I plug in my variables here and make sure to square root, sometimes we forget, you should get 0.03. And then when I divide these two numbers, I get 2 for my z-value. So in part D, it asks, what is the probability of having 16 or more damaged peaches in the sample? In other words, it's asking, what's the probability of having 0.16 or greater? So looking at our normal distribution in Excel, this is a greater than scenario. So I'm going to use this formula, 1 minus our norm.s.dist. So typing in equals 1 minus norm.s.dist, parentheses, the z-value we found in part C was 2. I'll type in comma, true, close my parentheses, and when I hit enter, I get 0.0228. So if you have any questions about chapter 6 or 7, just let me know.